I'm going to give you more of a report from the trenches. I would like to share with you some of my experience from being part of a deep learning project for the last 2 years. I'm going to focus on the human side of deep learning and the human side of what we need to attend to in order to make successful systems. And in some way, André and Ole has already sort of taken the words out of my mouth. But, you know, it never hurts to hear things twice, so don't worry. So there are very many problems that we could attend to in the world, and blindness is one that would be really good to try to tackle. The disease that is called diabetic retinopathy is the leading cause of blindness among working-aged adults. It accounts for 5% total of blindness in the world. And it has been designated as a priority eye disease by WHO. Diabetic retinopathy causes blindness if left unchecked. But if identified very early on, it can be halted by very inexpensive drugs. And later, if it gets worse, you may be able to deal with it by shooting some laser. It doesn't sound good, but it's better than going blind. But at some point, options are out, and you will go blind. And the worst part of this is that the patient will often not see anything until it's way too late. So early detection and intervention is assumed to actually be able to reduce blindness 90%. That's pretty good. But there are not enough doctors to do that detection. There's also perhaps a problem in having doctors do the intervention, but let us focus here on the detection. As a result, for instance, in India, about 45% of the people who turns up at the clinic with vision loss, they have never been diagnosed before. In eye care, one way that we can stretch some of the resources is actually by having trained photographers take a photo of the inside of your eye, the retina. And these photos, they look a little like these examples. On your left-hand side is a perfectly healthy eye. On the right-hand side is somebody with what we call moderate level of diabetic retinopathy. The photo shows the bleedings. The blood has started leaking out of the veins. And as the disease progresses, more leakage occur. And at some point, then these the blood flow starts to get really messed up. And that is when the person goes blind. An eye specialist would, by looking at these photos, be able to say that the person on the right-hand side needs some intervention. But the lack of local eye specialists has been partly mitigated by the existence of called teleretina services. That because now the photos of the retina is available, they can be transmitted to some place where there are people who can actually do the diagnosis. Often, for instance, in Africa and in India, they have to send the photos to pro bono reading centers, for instance, in England, and often it can take 48 hours, perhaps even a week, before you get the answer back. And unfortunately, at that point, the patient might long be gone and be hard to get hold on again. This interesting challenge was really inspiring one research scientist at Google in 2014. So he started what we call a 20% project, where he, next to his main job, actually started looking at whether he could use deep learning techniques on a huge set of retina images that he had gotten hold on. We have already heard a little bit about what deep learning is. I'll just frame it in terms of some of the buzzwords. The artificial intelligence is the big thing. It's sort of a vision, an idea. It was back in the 60s. We hoped that we could actually create a non-human intelligence. One of the more promising approaches to try to realize that dream has been machine learning. And we have seen a lot of wonderful work which is based on that instead of having to tell the machine every little detail that it needs to know, we instead teach the system how to learn by looking at the data that comes in. It learns by itself. And deep learning is one rather new, as we heard, rather new variation on machine learning. It's actually not that new. It's really the same as neural networks that we first, I think, heard about in the 80s, where it was really successful in sort of little toy examples. And that's actually the point. At that point, we were able to do only toy examples. What has happened meanwhile is that now we have cloud, we have a huge processing capability. Now we can actually do neural networks in many, many, many layers, and we can distribute the computing out throughout the world. Back to the Retina project. The project soon attracted a lot of interest from other volunteers in Google. And after about a year of intense work, there was a first model that seemed to be really, really promising. And as it turned out, clinical tests confirmed that we actually had a good performance and we had really, really good accuracy. There's something we talk about, the F-score, which is about positive, true positive, true negatives. And our algorithm, or his algorithm, actually managed to get a score of 0.95, whereas the human ophthalmologists, who were really expert ophthalmologists, they only reached a score of 0.91. A paper on this validation was accepted at the prestigious medical journal JAMA and published late 2016. So this is really a success. Right? We've saved the world, right? Not so fast. One thing is validation of the algorithm. That's okay. The other is to actually demonstrate that it's clinically relevant. And that is that the product concept makes sense to the medical profession in practice, that it makes some difference to the patients. So one aspect of this clinical relevance is whether this the automated the automated evaluation would have any impact. I mentioned earlier this point that early detection and treatment is key. With our algorithm, we could take and photo screen everybody, right? And then we could possibly, reduce the blindness with 90% as it was estimated. But the problem is a review of actual screening, photo screening of diabetic patients today shows some rather disturbing numbers, namely that less than 30% of the people who have been screened and found to have vision-threatening diabetic retinopathy, they will not see a specialist. They will not get the treatment that is necessary for them to preserve their eyesight. And another bad number is that when you are diabetic, you are often, or hopefully, told that you need to really attend regular eye exams, or at least eye screenings. Once a year, you need to go and get checked. If you actually get the disease, you may need to go more often. But what this study found was that less than 50% of these early stage patients would show up for the third or later annual screening. That's not good, because that was exactly the people we needed to get hold on so they don't go blind. So, what now? Should we just throw up our hands and be despair and go home? No. Let's try to see what we can do to understand what's going on and see if there's any part of this that we can actually have an influence on. And this is where the human side of deep learning comes in. We do what we call mapping and charting of the domain, and here what we did was we went to 2 different countries to understand photo screening. We went to California and to Tamil Nadu in India. The idea was to try to uncover the stories behind the 30% and the 50%. And, of course, to see if we could make the screening more impactful. This is just about that we visited a lot of clinics, but at the same time, please remember, this study is what we call a qualitative study. We are not trying to get some statistically valid data about anything. We are trying to figure out what are the real relevant questions to ask. What we came home with was that, yes, there is an issue of automated diagnosis alone will perhaps speed up the response time and therefore capture a few more people, but it will in itself not have the desired impact. We need to also add something about the situation in which the screening happens. And one of the things we found was that screening has to be brought to the people in some reasonable, sustainable way. That means, for instance, that if we can bring screening to where people are anyway, and where they have a little time, then they may actually sort of see it as innocent as just getting your blood pressure taken. And that speaks to something that became very clear speaking with all the patients. It is that the early stage patients, they really dislike thinking of themselves as sick. They have diabetes, yes, but after they first realized that and got to peace with it, then they don't want to think about themselves as sick. And that means that they don't want to go to hospitals. They don't want to, constantly be reminded that they are not as perfect as they should be. So this was a little bit about mapping and charting the domain, an example of that. Other things we do when we go out is that we try to understand the workflow, the sentiments around the activity we are studying, so that we can bring this information back to the team at home. It turns out that it's really also important for us to do this work, because in this way we tell the clinics, the physicians, the patients out there that we are really truly caring about how they feel and how their current situation is working. And that actually spills back in increased trust in us, and it helps us get access to come out and really try out some of our ideas in their clinical settings. Another side of the human side of deep learning that we are focusing on is more in the interaction design area. Let me say that the first part, the mapping and charting of the domain, that's not at all unique to deep learning. That's something we really ought to do in any kind of IT system. And in interaction design, you may say that's also, classical, well-known stuff. Although, hey, what am I talking about? Am I talking about an interface? Isn't the neural network just a little thing deep inside the system? Is there any interface at all? Well, yes, there is. And, that is where we can also use our traditional user interaction design, because it turns out that at least in this phase of the technology, when we build a deep learning system, we build many subsystems and side systems and whatnot, because, for instance, data comes in, data needs to be labeled. Often we have to do the labeling, and that means that we have to build a labeling interface that is really solid and good for these labelers. Also, I already talked about all these partners we need to work with, and in order to get them engaged, we need to show them what we have, so we have to create a demo interface. As soon as we go out in any clinical deployment, even if our thing is just an API call somewhere in their system, then we need to have reports that we create to clinicians and so on. But I think that even more exciting is the role that deep learning models have in skilled activity. That will call for new ways of thinking about interaction models or interaction modes. We actually inspired from regulatory terminology. When you need to get your medical piece of equipment approved by FDA, you have to say what class of medical device it is, and there you have to specify intended use. And we took that actually as a very helpful starting point for talking about the different roles that a deep learning-based system could have relative to the medical expert. And one is as assisted assessment, where we basically have our system work concurrently with a human expert. And we need really to figure out how can we, in this way, arrange the interaction to help clinicians do what they do, but do it much better than they're currently doing. Another way of seeing the role is by talking about preliminary assessment. So first, our system does something, come up with a suggestion, and then a human will see it. And that could be useful, for instance, in triaging. So you can sort the people in the waiting room. The final one is fully automated. That is sort of the most extreme, and that's where we really have to trust that system. It's working alone. It's working without human interaction, human specialist interaction, that is. Where would that be relevant? Yeah, for instance, we talked about this resource scarcity of doctors. It would be really helpful if we could put the algorithm into the screening process and therefore thereby relieve a lot of highly skilled people to do more interesting, more demanding things. Another is that there are many things that machines are not really good at, that machines are good at and humans are not really good at, and that is another place. Finally, there is a human aspect of modeling quality. And we have already touched on it in previous talks. One is the point that no amount of engineering smarts will overcome bad data and badly labeled data. That's just it. Garbage in, garbage out. Now, I have to just remind you here about data and labels. The way deep learning works is that you have kind of pairs of data elements and labels. And label is kind of the answer. And then in diabetic retinopathy, it would be the photo, the fundus photo, that would be the data, and moderate diabetic retinopathy would be the label. And we need to be able to make a data set where the labeling is consistent and consistent with some sort of gold standard. It gets really hairy because what is the gold standard? I don't have time to go into it here, but this colorful band is actually showing a depressive story about integrator disagreement. Same patient can get 4 different diagnoses on the same image. The final part is that we really need to remember when we interpret the results from a model that it is artificial neural networks. We do not really know exactly how they work. And just because we can see red spots and so on, and we can say, oh, that's moderate retinopathy, that doesn't mean that that is exactly what the neural network does. So we need to understand how to tell people what exactly they get out of the model. What is the result that they're seeing? What is the basis for it? For instance, if the model has only been trained on Caucasian eyes, and you come in with Asian eyes, you get really in trouble. You cannot trust that result because the model was not trained on the population that you are now bringing data in from. That could be a dangerous part as we go into clinical settings where not everybody may understand the complete consequences of statistic methods. Finally, I think that what I would like to leave you with is that this is a lot of work in progress, but we have found so far that there are at least 3 things that we need to understand in order to be successful. And that is that we need to do collaboration and collaboration and collaboration. Inside the team, we need to have lots of disciplines. All are relevant. We need to have partners outside because we cannot go it alone. And we need the human experts because they are the people who are going to, save us in the future. So we need to help them and figure out how they best collaborate with the systems. Thank you.